Until now, we've been looking at this simple model of reaction times using a normal likelihood. But as I showed you in the very beginning, when I plotted the data, there's a skew to the right in the data. And when you have this kind of positively, distributed data with no data points below zero and with this skew to one side, often a better likelihood function to use is the log normal likelihood function. So let's take a look at that and see what that brings to the table, right? So first of all, what is a log normal likelihood? This is just another probability density function or another type of random variable, if you want to think of it in those terms. So the idea here is that if some data is log normally distributed, then what that means is that the log of that data is normally distributed, right? So y would be the reaction times that we're talking about, and if I assert or if I hypothesize that this is log normally distributed, then taking the log of the reaction times would give me a normal distribution, right? So basically the relationship between the log normal and the normal is stated here, right? If y is log normally distributed, right, then what you could do is you could take the log of the observed data, right? This y is always in milliseconds, right? So you could take log milliseconds and that would be normally distributed then, right? That's the important thing here. So one important change that this entails is that the mu and sigma parameters are now on the log millisecond scale, right? We are now talking about these parameters on the log millisecond scale and the observed data is on the millisecond scale, right? And what this kind of distribution will do is that it will generate a typical skewed data set. The reaction times will have this typical skew that you actually observe in reaction time data, right? So there's an example of generating some data from simulated data from the log normal, right? So how do I do this? I define some parameters mu and sigma on the log scale. Okay, so 6 log milliseconds. What would that be in milliseconds? Just take the exponent of 6. That would be the time, reaction time in milliseconds, right? So I'm generating 50,000, or is it 500,000? 500,000 samples, right? 500,000 samples using a function called the RL norm function, right? So you see again the dpqr functions in action. I can generate simulated data from a log normal. I specify the mu and sigma and the number of data points, and I get simulated data here. And this is what it looks like, right? So now this log normal distribution seems to be a pretty reasonable way to talk about reaction times. It has this characteristic skew, the data are all positive, it's all good, right? So that's why whenever one does analysis with things like reaction time and so on, which are positively skewed, you generally use log normal likelihood because it's a much more reasonable representation of the generative process. Okay. All right, so let's start by refitting the model with a log normal likelihood this time. We have the same parameters, but these parameters now have to be defined on the log scale. The priors have to be defined on the log scale. This is a very common mistake that people make. They use a log normal likelihood, but they forget that the parameters are no longer on the millisecond scale. So they will use priors. A common mistake is to use a uniform prior going from 0 to 60,000. On the log scale, that's a gigantic range, okay? Try to figure out what the exponent of 60,000 would be, okay? So that's why it's very important to figure out what priors you should use on the log scale. So we start with very vague priors going from 0 to 11 on the uniform, using a uniform for mu, and for sigma we'll use a uniform going from 0 to 1, right? That's a pretty vague prior, an uninformative prior for the log normal here. Right? So you can of course verify that. What I just said, you can verify that by generating the prior predictive distribution, right? So how would I do that? Right? So here's some code for this. In the textbook, we give this function, normal predictive distribution function. All that is doing is very simple, right? It's just generating samples, right? We just get some samples from a uniform for the particular prior that we have for mu and the prior we have for sigma. So this is a vector of samples, right? How many? 1,000 samples here, right? for each of these data points, and I just plug them into this function, which takes these samples and just generates this function simply generates some observed data, right? It's a very simple function that produces this data, and then you will get this data and you can look at the properties of this data. So let's look at the properties of this prior predictive data under this prior specification that I have. So what I've done here is that I'm showing you some statistics of the prior predictive distributions. I've generated multiple data sets, and I'm going to look at the distribution of the mean reading times of those simulated data sets, multiple data sets, right? So the distribution of the mean reading times is pretty broad. As you can see, this is so broad. Why? Because the prior specifications are so vague, right? And so we're getting a broad range of variation, very large values. If you look at these response times in milliseconds, these are gigantic mean reading times, that we are getting from the predicted data. So the prior specification is completely absurd, even though it's not really going to matter in terms of looking at the posterior, because the posterior will not be heavily affected by the prior specification because we have sufficient data. But that's not always the case. We sometimes have very sparse data. In that case, the prior specification can be very important and can have important implications for the interpretation of the data. So similarly, if I look at the median reading times in the simulated data sets, pretty broad variation. The minimum and maximum reading times also vary very heavily across the data sets. So the priors are not super great, but that's fine. It's a good starting point, right? It's always fine to try out different priors to see what happens and which priors make more sense given the problem that you're working on. What one can do is one can come up with more reasonable priors for this kind of log normal likelihood, and that's what I will talk about next.